So now we are dealing with the torque acting on the rectangular coil carrying current placed in the presence of external magnetic field. Earlier we dealt about the force acting on unit charge unit charge moving in the presence of external magnetic field. Then we saw about the force acting on current carrying conductor. Now we are for rectangular coil. Now see, this topic is a bit confusing. It's very easy, but it's a bit confusing. Okay, when you will see a number of books, you will find other things done there. When you will see the notebook, you will find that it is a long description given here. Okay, but I thought that this long description is not necessary. Like this paragraph and this paragraph, it is unnecessary here. It's just for explanation. So when I checked a number of books, I found that I was correct. Like, see, in this book, this is the names book. Okay, so when this question was asked, it is just that a figure is drawn. Okay, figure. Now see, figure कोई भी बना सकते हैं. Here one figure is there in book. You will find this figure. Here you will find this figure. Okay, but I'll tell you which figure is much easier. So see, when I saw that a figure was there and the last paragraph, this last paragraph was just there, and then the derivation. Okay, so it is very simple. इतना ही किया हुआ है. So we'll also deal this much. Okay, still if you want to understand these both paragraphs, okay, I'll tell this after the video so that you don't get confused and you will watch it on your will only. So let's start this. So see, I'll tell you which figure to make. This is a torque acting on a rectangular coil. First we need to understand this. What is this topic? So see, this is a rectangular coil. Okay, here a rectangular coil. Remember, this is not the figure you need to make. This is just for explanation. This is a rectangular coil carrying current. Okay, it is carrying current. Okay, so now see PQRS, or you can name it ABCD, anything. Okay, we'll name it PQRS for our ease. Now see, while making figure, remember it will PQ will carry current in this direction. Okay, now this is not necessary. You can make in this direction also, but still we are making in this direction. This is not a thing to remember. Still, PQRS, it doesn't matter at all. PQRS, it is carrying current. Okay, now see, for this we need to understand the Fleming's left hand rule. I'm gonna deal about it. Now see, it is a rectangular coil carrying current. Its length is L and its breadth is B. Okay, its breadth is B. Now see, it is a rectangular coil. Now when it is acted upon by a magnetic force, okay, it means magnetic line of forces are there. These are the magnetic lines of forces B. When it is acted upon, now see, जैसे कि यहाँ पे अगर force लगेगा, so you'll think that force will be in this direction. This is the field, okay, B. And when it is striking here, you will think that force will be in this direction, but it is not the thing. Now see, here the Fleming's left hand rule will come into application. So see, this is a magnetic field B. There is current I, so the direction of the force F, in which direction the force is being acted, it will be given by the Fleming's left hand rule. Now for this we need to understand the Fleming's left hand rule. So see, I'm gonna say what is the Fleming's left hand rule. So for this we need to understand that Fleming's left hand rule, it is used to obtain the direction of force which is acting upon a current carrying conductor, okay, when it is placed in the presence of external magnetic field. Now according to this rule, the three fingers, which is the thumb, the index finger and the middle finger, thumb, index and middle finger, okay, this will represent a number of things. Like see, this middle finger, it is representing the direction of current. Okay, it will represent the direction of current. The index finger, it will represent the direction of magnetic field, and this thumb will give the direction of the force. So see, this is the direction of current. Remember, current, magnetic field, and this thumb, it will give the direction of force. Now see, if we can see that if this is the current, okay, current is in this direction and magnetic field is in that direction, then force will be means outwards, in upwards direction. Okay, force will be in this direction. So similarly, see here, the magnetic field B is in this direction, current is in this direction, so force will be in which direction? Also you see, current is in this direction. Okay, current is in this direction and force is in opposite direction. So force is in downwards direction. Okay, so see, magnetic field this direction, so thumb, so index finger, magnetic field, current is in this direction, so magnetic field will be in this direction, upward direction. This is the Fleming's left hand rule. Upwards means out of the paper, okay. Here upwards means out of the paper, obviously, but we cannot make out of the paper, okay. This, it will be in outwards direction, outwards, out of the paper, so we cannot make this. We'll make this in like this, okay. This is the force, direction of force, outwards. This means outwards, because see, magnetic field is in this direction, current is in this direction, and this is outwards. Similarly, when we go for this one, so see, current is in upwards direction, okay, like this, that's that direction, and magnetic field is in this direction, so current will be, so force will be in inwards, inside the paper. See, current that side, magnetic field this side, so force will be inside the paper. Inside the paper we cannot make, so we'll make like this, okay. This is the force inside the paper. So like this we obtained a direction of force. We were thinking that force will be in this direction, but no, force will be in this direction, okay. Similarly, when we calculate of these two, it will come like this, it will come like this. You can calculate, for instance, but I wrote directly. So these are the directions of force, okay. But now see, here this is the direction of force in normal condition. Normal condition means when it is placed perpendicular. Now see, in rectangular coil, what is the meaning of perpendicular and what is the meaning of this parallel, okay. See, this is the magnetic field, okay. ये एक magnetic field है, okay. This assume that magnetic field is in this direction, okay. These are the magnetic field in this direction. So when the coil, this is my coil, okay, when the coil is placed this way, it is called perpendicular, okay. But when the coil is placed this way, this is parallel to the field, okay. See, magnetic field is in this direction, like this, magnetic field is like this, and when the coil is placed like this, okay, then it is called perpendicular to the direction of the field. And when it is placed in the direction of magnetic field like this, then it is called parallel. So I said that I'll deal about it in at last, but I said these both paragraphs are dealing about it, in which direction the force will be when it is parallel and when it is perpendicular. But it is not needed, okay, because this question will be asked when the torque, to calculate the torque when it will make an angle theta with the magnetic field. No perpendicular, no parallel, it will make an angle theta. मतलब ये theta condition के लिए, when it is making an angle, when this rectangular coil is making an angle theta with the field, उस condition के लिए निकालने के लिए बोल रहे. Because our final expression is also see BINA cos theta, it is asking for theta, so there is no need for perpendicular and parallel explanations, okay. So I said that it is not needed. एग्जाम क्यों लंबा करना हो, बस कन्फ्यूजन भी होगा, so will not deal about it, okay. Still I'll say at last. Now see, so I said this is not the figure to make, this is for a normal condition, this is for a perpendicular condition. See, it is magnetic field is perpendicular like this, so this is not we are dealing about. We are dealing about this figure, when it is making angle theta. Now see how it will make angle theta. See, as I said, this is the direction of magnetic field, this is the direction of magnetic field, this is the condition for parallel, okay. This is the condition for parallel, this is a magnetic field, this is parallel. But when it will make an angle like this, okay, it will become, so see, it is slanted, a bit slanted. Now this is the condition for parallel. This is my magnetic field, okay, this is a magnetic field in this direction. See, parallel will be like this, perpendicular will be like this. When it is parallel and making angle theta like this, okay, it is making an angle theta, it is slanted, okay, it is slanted. See, there is a gap, this is slanted. So this is the condition when this rectangular coil is making an angle theta. This angle is theta, this is the angle theta. This is what we need to derive. So see, this is our magnetic field, okay, this is our magnetic field, and now our coil is making an angle theta. So if this is our coil, it will make an angle theta, okay. Now this angle will become theta, this is the angle theta, this is B, this is PQRS, so this will be our angle theta. And similar, this, it is carrying current I, this is also carrying current I in this direction, okay. So I'll make a bit clear figure. So see, it is magnetic field B, this is the figure you need to make, okay, this is the figure you need to make. Like this will make a bit slanted, okay, even here we'll make one magnetic field. So PQRS, it is making an angle theta. Okay, it is making an angle theta. Now see, it is carrying current I. Okay, in this direction. It is L, it is B. You can note down the figure if you want. It is B. Okay, now see, when it is going this way, force is acting in this direction. As I said, force is acting in this direction. I explained how force is acting in this direction outside the paper. Force is acting outside the paper. Even here the force is acting inside the paper. Okay, force is acting inside the paper. Now here the force is acting outwards. The force is acting this way. Okay, this will be F1, F2, F3, F4. So this is the basic figure. Okay, now we know that F1, F2, F3, F4. Now I'm explaining the paragraph what we need to write. You can see the last paragraph. Okay, so when the coil makes an angle theta with the direction of the field, the force acting along the segments PS and QR are equal in magnitude, opposite in direction, and acts along the same line, which cancels the effect of each other. Now see, it is dealing about PS and QR. Okay, see, PS and QR are equal in magnitude, opposite in direction, and they are acting along the same line. Same line means, see, it is acting along the same line. Okay, same line of action of force. So these both will cancel each other, but these two, they are equal in magnitude, opposite in direction, but they are not acting along the same line. One is outwards the paper, and another is inwards the paper. Okay, they are not acting along the same line, so it will not cancel each other. Instead it will produce a couple. See, it is acting this way and it is acting that way, so it will produce a couple, and this will cause a turning effect. Okay, now see, I'll explain how it will cause a turning effect. Suppose this is a wait suppose this is the magnetic field in this direction. Okay, now see, this is the magnetic field in that direction, and I'm taking a ruler. For instance, this is a coil. Okay, and it is placed like this. Okay, making angle theta. It is placed like this, making angle theta. Now see, in this direction and in this direction, okay, in that direction and in this direction, they're acting along the same line, opposite and equal in magnitude, so it will cancel each other. But these both, okay, they are not acting along the same line. One is acting outwards and one is acting inwards. Okay, now see, for instance, this is our magnetic field and this is our coil. It is making an angle theta. Okay, this is the angle theta. It is an angle theta. So now see, as per our rule, Fleming's left hand rule, this will be current is in this direction, magnetic field is in that direction, so force will be outwards. Similarly inwards, so it is outwards and this is inwards and outwards. So now see, force so now, as I said, one is outwards, one is inwards. So see, outwards will when it is outwards, it will go in this direction. Force is in this direction, so it will move in this direction, and it is inward, it will go in this direction. So in this way, this turning effect or torque is produced. See, it was like this, outwards, inwards. Okay, when it is outwards, it will go in this, and it is inwards, it will go in this direction. So this way, it will turn. So this is the turning effect of force, and that is the torque which is produced. And we need to find the value of this torque produced. Okay, we need to find the expression of this torque produced. Okay, so that is our basic thing. So I made you understand what is a torque and what is the figure we need to make. Now let's go for the expression. Okay, so this is the figure we need to make, and last one thing, so also a clear figure which we need to make. Okay, we need to make two figures here. See, first figure, the same figure I am drawing here. So this is the figure we need to make. You can copy the figure or screenshot the figure if you want. Okay, this is the first figure we need to make, figure 1. Okay, and now second figure we need to make, which is of the top view. Okay, the top view. So I'll show you this. This is the top view. Now see, what is this? So see, we are taking the view of this QR. Okay, we are taking the view in the notebook. This figure is the top view. Okay, here it is more clear. We are taking the view of QR. Okay, QR. Like see, if we assume this to be the rectangular coil, this will be PQRS. So this will be QR. Okay, so we are seeing the top view like this, QR. Okay, so see, this is the magnetic field in this direction, and when we see QR, we'll see it in this way, isn't it? We'll see it this way. So we are seeing QR in this way. If we see the QR, it will be in this way. So Q and R will make QR. Okay, and then here it is normal. This will be the normal. So this is the normal. So this is the normal. It is making an angle theta. Okay, with the normal. Actually, these are the normals. They are the magnetic lines of forces. So B, these are the magnetic lines of forces. B. So see, normal making an angle theta. Here we can write theta here. It is making angle theta. And when we join this, okay, so this will become. We'll assume this to be, as in notebook, M, and this is Q R, isn't it? And let us assume M. Okay, so if we join this, it will become this RM. The value of RM will be, so this RM is the perpendicular, and this is QRM. It is just to think that this face is QR. Okay, this face QR. So we are making this face as top view. This is QR. When we see QR, then it will be making, this is our magnetic field. Okay, this is our magnetic field, and this is QR. So we are seeing this from top view like this. So this is the angle theta, and when we join this, so this will become our QR cos theta. Now how it will become QR cos theta? See, it is theta. Okay, so cos theta will be B by H. So B will be here QM by QR. So see, QM will become QR cos theta. So this QM means QR cos theta. Okay, this is all about the figure we need to make. First of all, we'll make these two figures. Okay, and then we'll do the description, only the last paragraph description. Okay, and then we'll go for the derivation. Now the derivation is very easy. We know easily. Torque means what? It is the force into perpendicular distance. Okay, torque means force into perpendicular distance. So see, force into perpendicular distance. Now we know force here will be, if we assume it to be a straight conductor, only if we'll take only one face, so it will be BIL sin theta. Okay, BIL sin theta, not here, it will be 90 degree. I'll show you why. First of all, let me clear why it is BIL sin 90 degree. See, as we do, it is BQ sin theta for an unit charge, and BIL sin theta for a current carrying conductor. If we take only this face QR, okay, so it will be a single conductor carrying current. Okay, single conductor carrying current. So it will become F will become BIL sin 90 degree, because we are taking perpendicular distance into, now see here, perpendicular distance between the line of action of force. So see, and perpendicular distance will be this QM. Okay, this is the perpendicular distance QM. Now what is the perpendicular distance between the lines of action of forces? It is written perpendicular distance between the line of action of force. See, QR में force इस direction में act हो रहा है, R में force इस direction. So this and this is the line of action of force. Perpendicular distance between them is QM. So it will become QM. Okay, while derivation we just need to do this figure, both the figures. Okay, and then description and this short derivation. It will be merely one page. So see, I'm just explaining. So this Q and R, Q में force इस side, R में force this side. Okay, so see, these both are the lines of action of forces. See, Q में force इस side act कर रहा है ना. Okay, and इस side इसमें act कर रहा है. So see, here it will be this side, here it will be this side. Okay, so these both, this is the line, perpendicular distance between them, a line of action of force, which is QM. We have joined this, isn't it? We have joined this QM. See, enlarged figure of this QM. So see, perpendicular distance become QM. BIL sin 90 degree, because we are taking the perpendicular distance. Now see, BIL sin 90 degree is 1, and now see, QM means, we calculated QM means QR cos theta. So QM means QR cos theta. We can directly write it, or in bracket we can write that cos theta means QM by QR. So QM becomes QR cos theta. Okay, simple. And now see, it will be BI L. Now see QR is what? If you see QR, it is the breadth. How it is breadth? See, this is length, okay, this is length, and this is breadth, isn't it? We said at first this is length, this is breadth, length, breadth. In figure also we have made. So this is breadth, this is breadth. So QR is also breadth B. Length, breadth. QR is breadth B. QR means B cos theta, breadth, and L into B is A, so it will become BIA cos theta. Okay, torque will be BIA cos theta. This is our expression, and if there are n number of rectangular coils, then it will become, this will become BINA cos theta. So this is our final expression. Only this much derivation, just these two figures, one small paragraph, and this is all about the torque acting upon rectangular coil. We understood? Okay, you understood this? It is just making an angle theta. Okay, it is making angle theta. From Fleming's left hand rule, it will be outwards, it will be inwards, it will be outward, inwards. So it will just turn like this, it will turn like this, and then we'll take the top view, we'll just join this, okay. So the perpendicular distance between the line of action of force, which is QM, isn't it? See, torque is force into perpendicular distance, easy, but the perpendicular distance here we need to calculate now. Perpendicular distance, so we are joining this, we need to calculate perpendicular distance between the line of action of force. We are taking face Q, so line of action of force QM, so QM means QR cos theta, and BL sin 90 degree. Now see, QR means B, this is length, this is breadth, isn't it? Length, breadth. So QR means B, and finally this expression came. Special cases, we know if theta, if it is parallel, if the plane of the coil is parallel to the direction theta equal to 0 degree, so it will become BINA cos 0 degree, which will be which is BINA, which will be the maximum. And then if it is perpendicular, then 90 degree, it will be 0 minimum. Okay, this is all about the torque acting on the rectangular coil carrying current.